What specific problem does the proposed Titans architecture aim to solve, and why is this problem significant in the context of current transformer models?
The proposed Titans architecture aims to address the significant problem of scalability and memory management in current transformer models, particularly when dealing with very long context sequences. Transformers exhibit quadratic time and memory complexity, which limits their applicability in real-world tasks that require processing extensive data, such as language modeling and time series forecasting. Titans introduces a long-term neural memory module that learns to memorize and manage information effectively at test time, allowing it to scale beyond the 2M context window size typical of transformers. This architecture incorporates distinct memory modules, short-term, long-term, and persistent memory, enabling better generalization and efficient retrieval of relevant information. By overcoming the limitations of traditional transformers, Titans enhances performance across various tasks while maintaining efficiency, making it a significant advancement in the field.
How does the proposed method or algorithm work? Illustrate step by step, particularly focusing on the long-term memory modules functioning during the training phase.
The proposed method introduces a long-term neural memory module that learns to memorize and store data during the test phase. Initially, the model treats the training as an online learning problem, where it compresses past information into the parameters of the long-term memory module. The key innovation is the use of a surprise metric, defined as the gradient of the neural network with respect to the input, which helps the model identify and prioritize surprising inputs for memorization. During training, the memory is updated using a combination of past and momentary surprise metrics, allowing the model to adaptively manage what information to retain or forget through a gating mechanism. This process enables the memory module to effectively learn associations between keys and values, optimizing an associative memory loss function to enhance its performance in various tasks.
Can you provide a simple yet illustrative example that demonstrates how the Titans architecture effectively memorizes and retrieves information using its long-term memory module?
The Titans architecture utilizes its long-term memory module to effectively memorize and retrieve information by treating incoming data segments as current contexts while referencing historical information stored in memory. For instance, when processing a long sequence, the architecture first chunks the sequence into fixed-size segments. Upon receiving a new segment, it retrieves relevant past information from the long-term memory, using the current segment as a query. This retrieval process is facilitated by an attention mechanism that helps the model determine which historical data is pertinent, thereby preventing memory overflow by only storing useful information. Consequently, during inference, the model can access this stored information to enhance its understanding and response to the current context, demonstrating a dynamic and efficient memory management system.
What are the theoretical or practical benefits of using this Titans architecture over traditional transformer models and linear recurrent models?
The Titans architecture offers several theoretical and practical benefits over traditional transformer models and linear recurrent models. Firstly, Titans can effectively scale to context lengths exceeding 2 million tokens, which is a significant limitation for standard transformers due to their quadratic complexity in memory and time. Secondly, the architecture incorporates a deep neural long-term memory module that learns to memorize and manage information at test time, allowing for better generalization and memory management compared to linear recurrent models that compress historical data into fixed-size memory. Additionally, Titans outperform modern recurrent models and their hybrid variants in various tasks, including language modeling and common sense reasoning, demonstrating superior performance metrics such as perplexity and accuracy. Lastly, the design of Titans, particularly the memory as a context variant, allows for the retrieval of relevant historical information, enhancing the model's ability to handle long dependencies effectively, which is often a challenge for traditional architectures.
How is the performance of the Titans architecture validated? Describe the experimental design, datasets used, and metrics for performance that clearly demonstrate its effectiveness.
The performance of the Titan's architecture is validated through a series of experimental evaluations across various tasks, including language modeling, common sense reasoning, needle and haystack, NEA, time series forecasting, and DNA modeling. The experimental design involves comparing Titans with state-of-the-art models, such as Transformer++, Gated Linear Attention, GLA, and Mamba, across different scales of parameters, 170M, 340M, 400M, and 760M, trained on large datasets like FineWebADO, which consists of 15B to 30B tokens. Metrics for performance include perplexity and accuracy in language tasks, as well as retrieval effectiveness in NEA tasks, where Titans consistently outperform baselines, demonstrating superior memory management and generalization capabilities. Additionally, Titans are evaluated on their ability to handle longer context windows, showing competitive performance even with context lengths exceeding 2M tokens, which highlights their scalability and efficiency. The results from these experiments, including ablation studies, further confirm the contributions of various architectural components to the overall effectiveness of the Titan's architecture.
What limitations or drawbacks did the authors identify for their proposed Titan's architecture, and how might these affect its applicability in real-world scenarios?
The authors identified several limitations of the Titan's architecture, particularly concerning its efficiency and scalability. Firstly, while Titans outperform existing models in various tasks, they noted that deeper memory modules, while more expressive, lead to slower training times, indicating a trade-off between effectiveness and efficiency. Additionally, the architecture's reliance on a complex memory management system, including mechanisms for forgetting and surprise metrics, may complicate its implementation in real-world applications where simplicity and speed are often prioritized. Furthermore, the authors acknowledged that Titans, despite their advantages, are slightly slower than some optimized models like Mamba 2, due to their deep memory structure and expressive transition processes. These factors could hinder the Titan's architecture's adoption in scenarios requiring rapid processing and real-time performance.